Well, good afternoon, ladies and gentlemen. We are Lucía Ballesteros, Ana González, and María Hermosilla, and we are honored to be here today. First of all, thank you to the Alba Orbital team for inviting us and for having all us here gathered together. And of course, thanks to you for being here listening to us. For the next 15 minutes, we will be talking about the attitude determination control subsystem that we are developing with COTS, commercial off-the-shelf components. And well, Anna, Lucia, and I are here as representation of our group. We are 16 engineers with mainly a background in aerospace engineering. And we are enrolled in the master degree of space systems in the Technical University of Madrid, for now on UPM, with the Instituto de Microgravedad Ignacio de Arribas, which is our research center. From now I'll call it IDR. And as individuals, that's what we are. And within the master program, we work in real space projects, hand in hand with our professors, which has given us a lot of experience while studying. And also, for example, what we have done in this course has been the integration and testing of our one-unit CubeSat, and also the design, manufacture, and testing of an adaptive system in composite materials. But let aside who we are as individuals, and let's pay attention to who we are as a team. And as a team, we are QubeeLab. QubeeLab is an association founded by us in our university to support students who want to keep on studying space stuff just like us, and also as a way to formalize our ideas and keep on working in this project that we are working on. So essentially, we're just engineers with this disruptive idea that we want to implement, and hopefully with it to contribute to the development of the PocketQube world.
Okay, so what is this disruptive idea that we are talking about? We are developing MagPi, which stands for Magnetic PocketQube. Oh, sorry. Here, Magnetic PocketQube in Orbit Experiment. MagPi consists in an active magnetic attitude determination and control subsystem based on COTS, commercial off-the-shelf components. It offers wider possibilities for PocketQube orientation than the actual developed ADCSs, all with the added bonus of a small size and a reduced power consumption. Sorry. Okay. Currently, the main advantage of PocketQubes over other satellites are precisely their small size and low price, making them highly accessible. Hence, they are a crucial aspect in the development of the new space. Nowadays, a lot of university-level researchers are opting for PocketQubes as their ideal platforms to demonstrate their technology or conduct experiments, as we have been seeing these past few days. Even commercially, entire constellations based on PocketQubes are being developed. For example, we have FOSSA systems with a constellation of 11 PocketQubes for IoT purposes, or, as it happens, Unicorn 2, designed by Alba Orbital. Nevertheless, the miniaturization of the subsystems for this new standard is a challenge itself. Regarding the ADCS, most PocketQubes are not equipped with one, but the ones that do usually carry a permanent magnet that tries to ensure that the PocketQube follows the Earth's magnetic field lines, which has its limitations. In case better attitude control is needed, you normally need to increase the size of the PocketQube to 2p or 3p, or to reduce the available volume for the payload. And either of the two options is inconvenient, let's be honest. But MagPi is here to solve all these problems. Okay, it is now time for a story. Okay, it is now time for the story. This idea was born when we were brainstorming ideas for a payload for a 1.5 PocketQube in the context of the Europe to Space Challenge. We were thinking of really great ideas that suited perfectly such small satellites, but at one point or another we needed some requirements concerning the pointing and the control attitude. So we started looking for commercial solutions, and as can be found for CubeSats, but we found nothing given the severe restrictions in power, budget, mass, and volume. So seeing this bigger picture, we thought, why don't we just develop one for this standard, and then in the future, these ideas will be feasible. So then we looked through the window and we saw a MagPi, and we thought, okay, let's do it. And long story short, we are here. We wanted to tell you that our proposal for the challenge is UPM Cube, in which MagPi is the payload. And also, it is worth mentioning that we won the challenge, and the reviews from the jury were really positive. And this meant a lot to us, considering that the jury was formed by the co-creators of the CubeSat standard.
Okay, so let's talk about our proposal more in depth. As we have already mentioned, MagPi is an attitude determination and control subsystem, which principal feature is that it consists mainly of COTS. To be honest, MagPi's elements are pretty standard: a triaxial magnetometer, 3 magnetorquers, and solar sensors. Using COTS means not having to test everything that you buy, which significantly reduces the additional costs, and it's much more convenient for not too expensive projects as the ones that are developed by university-level researchers. Given our goal of building an ADCS affordable that can be implemented by other PocketQube developers as you in their platforms, using COTS is a key aspect of MagPi's development. Considering this, we have chosen the triaxial magnetometer and the solar sensors to be COTS. On the other hand, the 3 magnetorquers are not commercial components. In fact, they are built by our team so that we can adapt the coil size and their layout inside the platform to our needs. On the slide, you can see a 3D representation of the support that we have designed to host these 3 magnetorquers that will be 3D printed using EC++ approved materials. Still, MagPi's potential does not lie only on its components, but also in the control law and determination that is implemented inside. MagPi arises as the adaptation for PocketQubes of a control law that has already been tested and proven in space through the UPM Sat-2 mission. This control law is a strong starting point, and it is explained in the paper called Magnetic Attitude Control for Satellites in Sun-synchronous and Polar Orbits, whose authors are Javier Cubas, Santiago Pindado, who are researchers in the IDR, and also Asal Farahi. This paper was published in the American Institute of Aeronautics and Astronautics, to be more precisely in their first quarter journal of Dynamics, Control, and Guidance. So here, the main challenge has been fitting all the components in the smallest place available while achieving the power requirements, minimizing the mass, and also minimizing the occupied volume. Besides, unlike other ADCS, in MagPi, the determination and control functionalities are completely independent computed. In case for determination, measurements from the solar sensors are used, along with magnetic measurements taken with the magnetometer. On the other hand, the control part is completely magnetic, involving the magnetorquers and the magnetometer. According to the control algorithm implemented in MagPi, two types of orientations are available for the PocketQube. Type 1 orientation, in the type 1 orientation, the PocketQube follows the magnetic field lines, which is the same type of orientation achieved with a passive magnetic attitude, but with some advantages regarding the stability and the rotational speed. In type 2, no, not that one. That one, sorry. As I was saying, in type 2 orientation, the PocketQube has an axis which is normal to the orbital plane, and the rotational speed about that axis is also controlled. Moving on to the features of MagPi, the power consumption per orbit is estimated to be about 25 milliwatts. The maximum envelope is 40 by 40 by 20 millimeters, and its mass is 54 grams. Also, the control law has been implemented using Simulink, and it is ready to be translated into a C++ code. Moreover, as we have already mentioned, there are two types of orientations that can be chosen from the consumer, type 1 and type 2. And in a future iteration of the design, we are trying to include the functionality of changing from one type to another while in orbit.
Moving on to the advantages of MagPi, it has three, like the main ones. Firstly, the design is integral, which means that it can be implemented in any platform, because in our second iteration of the design, we are developing a microprocessor. And having that, then the ADCS could be independent from the onboard computer of the platform. Secondly, we will overcome the difficulties that passive attitude control systems and even some active ones, such as the B-dot control law, have. Because our ADCS, it's terminal, and you can control the rotation speed. So it could be feasible to have continuous contact links with the communication links, with the Earth, if the antenna is placed strategically. And finally, the third advantage is that it can be adapted to any bigger satellite platform. So this would mean decrease in the mass of the satellite, and also decrease in the power consumption, and also more room for the payload, which would increase the profit of the overall mission. Another essential key point of our project is that the control law and the solar sensors have already been tested in the UPM-SAT-2 in space. So this gives us this heritage that reduces significantly the risk of failure of the missions, since the TRL of the components is very high. We also want to talk about our supporters and sponsors. So they are the IDR, the one I've been talking about pretty much all the time, and the Technical University of Madrid and the Strauss Group. But mainly the ones who are supporting us economically and with access to their facilities are the IDR, since they have vacuum chambers and vibration testing rooms and clean rooms as well. So they are supporting us mainly. And well, let's go with the good news. And that's that we will be launching our MagPi inside the UPM-Cube satellite that we already talked about in 2024. So we are really excited about this opportunity that has come to us, and we really hope that it will be successful and that we will contribute to the development of this PocketQube world. So Magpie will be flying in the UPM-Cube satellite, and if you want, it could fly in your satellite too. Thank you very much for listening to us, and if you have any questions.